Welcome to Lesson 15, Density and Springs. This is the start of the materials topic, the physics of matter. Here's the plan for today. We start with density, which is the mass per unit volume, and given by the symbol ρ, which equals m/v, kilograms per cubic metre. Learn the words as well as the symbols, because mass per unit volume is often a mark in itself. Density can be thought of as how compact the material is. A higher density means the material is more compact. It's easy to get the mass of any object by putting it on a scale, but sometimes it can be hard to get the volume. There are three cases to look at. For a liquid, pour it into a measuring cylinder and read off the value. For a regular solid, just measure the dimensions and calculate. For an irregular solid, something awkwardly shaped, like a phone charger, you use displacement. If you place it into water and measure how much the water level rises, that volume of water is the volume of the object. An alloy is a material made from two or more elements. The density of the alloy is the total mass over the total volume, which means you add each material's density multiplied by its volume and divide by the total volume. It's essentially a weighted average, weighted by how much of each material there is. Now on to springs. Hang a weight on a spring and it stretches. Hooke's law says the extension is proportional to the force. F equals K delta L, where delta L is the extension and K is the spring constant. Let's think about what K actually means. It's the force needed per metre of extension, so its units are newtons per metre. A big K means a stiff spring that barely budges. A small k means a floppy one. And that proportionality means that the force extension graph is a straight line through the origin, with the gradient equal to k. That graph is worth being able to sketch instantly. Stretching a spring takes work, and that work is stored in the spring as elastic potential energy. But where do we find it? It's the area under the force extension graph, formally the integral of force with respect to extension. Since the graph is a straight line through the origin, that area is just a triangle, a half base times height, which is half f delta L. And because f equals k delta L, you can substitute it in to get half k delta L squared. Two forms of the same equation, just use whichever matches what the question gives you. Finally, combining springs. And the logic here is worth following, because it comes back almost identically when we do resistors in circuits. Springs in series, end to end, both carry the same force. The full weight passes through both, but each contributes its own extension, and those extensions add up. Work that through and you get 1 over the total k equals 1 over k1 plus 1 over k2. So springs in series make a floppier system, which makes sense. A longer chain of springs stretches further. Springs in parallel, however, side by side, both stretch the same amount, and they share the load between them. Add the forces and you find the total spring constant is simply K1 plus K2. Two springs side by side make a stiffer system. That's the end of the video. Next time we'll look at stress and strain. Thanks for watching. Check out my tutoring page below.